you on linked list. Hopefully I try to come up with a visualization that will hopefully be helpful and can help us think about this. I guess let's do from a scale 1 to 5. How comfortable do you feel with linked list in general? 5 being very confident, 1 being not confident at all. Can we have it in this Slack? No, yeah, in the chat. Okay. And decimal numbers too. Okay. Yeah, this is about maybe half a little bit nudging towards higher. That's good. That's definitely good, so that we can move on to sort of the review and the visualization quickly, and then we can solve some questions. Cool. So let me share my screen here, and as always, at any point, feel free to reach out with any questions. Just unmute yourself, or also raise your hand virtually, and I can see you. Can see what. Cool. So let me hide some of this stuff that we're going to talk about. Oops, not that one. Okay, I guess like actually let's start with some share out. Like, what do you remember about one? Any thoughts or comments about that? Just unmute yourself.
It has pointers.
Pointers is a keyword.
If you want to find a node inside the linked list, you got to go through the entire linked list to get there.
So to find something, you have to traverse.
You have to traverse through the head to the entire linked list until you find that node.
Mm-hmm. Cool. Anything else? Is it be enough? Through, I don't know how to spell this. I don't know if that's correct, but pointers. To find something, you have to traverse through the head. Anything else? What is
the speed? It's like pretty constant.
Speed?
Right? The speed at which you search through it or use the algorithm.
So like, there is implications in speed, and we can talk about that. I guess like it has a few advantages. For instance, one of the advantages is removing at the beginning, adding at the beginning, or removing the beginning, adding at the end, or removing at the end is O of 1. So let's do removal / add beginning / end is O of 1 operation, so it's constant time. How long does it take to add something at the beginning of an array in terms of big O notation? Oh, and is this being recorded? Let me make sure. Yeah, it is. How long does it take to to add something at the beginning of the array in terms of big O notation, how expensive that is in big O.
That's similar.
O of n, isn't it?
O of n, that's correct. Giselle.
Possible.
Why do you think it's O of n?
You have to rename the values for all the other elements in the array after that first initial value is given a certain, after you push that new value in. So if you already have, say, those elements in your array, and you decide to add the number 2 before 3, or shorter than whatever element, all the indexes for those existing elements in that array have to be moved up by 1 number. So each one has to be modified, as opposed to a linked list where you just change the pointers that point to that node, and there's no, you know, I guess you don't have to go through each individual node. So it's constant time add and removal, but linear time or O of n search through a linked list.
That's very true, very accurately described. That's correct. Like if we want to add these two at the beginning of this array, what we need to do is move everything in one place, right? That's gonna, that's gonna take as many operations as the length or as elements in the array, right? So that ends up being O of 1. And we're gonna see once we have a linked list that could basically look like this. And we have a head pointing to this, right? The head pointing to this element. To add a new element, what we'll do conceptually is create a node first. Let's say the node with 2, and then point this node 2 to the all head, and then update. Oops, is this the tool that I want? Yeah. And then basically just, I think it's not working the tool, just update the head quickly here, and we get rid of this. And in that, that operation will take constant time, where on the array we have to shift everything one to the right or towards the end. Cool, so let me see. My computer seems to be running quite hot for some reason. Or like the fans like running. Let's see why. Oh, okay. Because I'm doing this. Cool. So we saw that. What is a disadvantage? A disadvantage of a linked list. Anyone can think of any?
It's not constant time lookup.
Yes, it's not constant time lookup. Let me see. Why isn't this letting me write anything? Sorry. Your selection. Okay. It is a disadvantage. Well, no constant time lookup. So no constant time lookup. What is something we know that has constant time lookup?
Arrays.
Correct. What else? What is Ben's favorite data structure?
Hash map.
Objects.
Hash maps. That's correct. They have, they have constant lookup because, well, the keys get hashed and that gets turned into an index where the value is at. Same in the array. You have the index. You can get it in constant time. Linked lists don't have indices. There is no way that we can access one node in constant time. As Cameron mentioned here, we need to find anything in it, we'll need to go through the entire list. I guess like lookup here, I think lookup can be a bit confusing word in the sense that, getting something in constant time, let's define lookup as getting something in constant time, where we know through hashing or through an index. Finding finding an element in the linked list or finding an element in the array will still be relevant because we have to go over all the possible values, searching for something, etc. So that's one. I think let's leave it here for now. So yes, these are very good points. So let's talk about how do we do that in JavaScript. So in JavaScript, to represent elements in the linked list, what we do is we create a node class like we have here. That has a constructor, it receives a value, and we just assign for a linked list, we need at least two things: a value to hold on to, and the next, a reference to the next node. And that's what is going to make it a linked list. I think I like to think of this as like a box, basically, that's divided into two, where we have a compartment for the value and the next. And that's sort of this drawing that I came up with. And more simply, we could just represent it with this square here, a value and the next division, and so on. Right now, the next is empty because we don't have a next as of yet. We haven't created a node yet. So how do we start creating these nodes? Oh, also, there's something else that I forgot to mention that I wanted to bring up. Linked list is an abstract data structure. What do you think that means? What does it mean to be an abstract data structure? Or what about the opposite of that question? What is a data structure that is not abstract?
Oh, I was going to say something that's simple on the outside, but more complex on the inside. Is that close?
Is that for is that for an abstract data structure or for a non-abstract data structure?
An abstract data structure.
So could you repeat that again?
Like something that's simple on the outside, but more complex on the inside. That makes sense.
Yeah, I think that applies. That applies here, and that is something that we as engineers try to do as well. Like, it might be all the programs you use, the browser and all that. That is incredibly complex in the inside, but yet regular people can use a browser. So that will apply here. That's still true here. But what else? Let's see.
Is it like it's not a defined data structure that has like defined rules and a defined structure, like an array, for example? Like it can be because it's like conceptual, it can be written in different ways. Is that why?
Yeah, I hold on to that. I want to take some notes of that. One is like simple on the outside. Complex inside. I think this still applies. So Savita, you mentioned like not defined, but not defined in the sense these data structures do have rules, but they're gonna have like they have specific rules, but there is room for there's wiggling room. I think that's what it's called, or what it's referred to. Like, and I think there was something that you said at the end. Do you remember what you said at the end, or the last part?
Well, I compared it to an array, where an array is something very specific and it's written in a specific way. And I said that this is conceptual. It's more conceptual. So as a result, there might be a few ways to write it, where an array, there's a very specific way to write it. But at least that's in my head how I think of linked lists, which is why they're confusing to me. They don't have the rigid rules that like something like an array would have.
That's correct. And I think that brings me also to the point that they're not built in.
Right.
You can think of it built in. they do not come with JavaScript. These data structures do not come with JavaScript. You know, arrays come with most, I think, all the languages that I have ever seen, because it's a fundamental data structure. And you could say, you know, a simple array, I would argue, is not an abstract data structure. You know, I guess it depends on what you mean by abstract. It is abstract in the sense that it's like these boxes inside of a computer memory, in, you know, ones and zeros, and that in that regard is abstract. But the abstract we're talking about here is like, yes, it's sort of more conceptual. There is a few ways to implement that could be valid. Mostly, I think this one is stellar. They're not built in. The developers create them, and all these abstract data structures build on top of the lower data structures like arrays. You know, for instance, hash maps. We have objects in JavaScript. That is technically a hash map. That is an abstract data structure. There are languages that do not have hash maps. You have to write your own, or there are libraries that write that. But you know, the simplest data structures like arrays, characters, strings, booleans. Those are, you know, even those are not even, at some point they're not even called data structures. They're just called data types. And if we think about, you know, I think this was somewhat confusing for me at first. Like, what does data structure mean? And can anyone like attempt to put a definition on data structure? Like, I guess maybe almost from the dictionary perspective.
Is it like a structured way to store?
That is correct. Could you say that again a little bit louder?
A structured way to store information.
Mm-hmm. Structure way. Storing info. That's correct. That is exactly what this is. Data structure is a structured way of storing information. By that, this structure speaks of certain rules and behaviors that we're going to see with linked list. And yeah, data structure is just a way of storing information. In an array, you store information a certain way. In a hash table, in an object, you store information a certain way. There's different rules. And saying that still applies to linked list. So this is very good. Any questions about what we have talked so far? Okay, so cool. So I think as Savita said, like that this is part of what makes it hard to wrap our head around. The fact that it's abstract, and I think I try to do a few drawings to remove some of that abstraction and utilize some analogies. That's actually was inspired by, I think somebody shared a React talk. I owe you sharing that in the Slack channel as well. I forgot her name, but she works at egghead.io, which is a they do courses like tech courses, like they teach React, they teach a few things, and she's an illustrator. And this was actually, I remember the name of the talk. If you can have the time, do watch it. The name of the talk is I think Woman of React 2020. If you put that on YouTube, you'll find it. I only saw her talk. I haven't seen the others. I don't even remember her name. I remember I replied to her on Twitter because she really inspired me to try to draw more and try to, you know, all this stuff is very abstract and just, you know, walls of text are hard to process. Those were some of the arguments that she made, and she creates analogies for tech concepts basically. And I owe her inspiration for this, and I think that's something that I want to do going forward, trying to do a lot more graphs and analogies for things like that. So that's where it came this box came from. But yeah, I'll share the link later on. Highly recommended. She explains a few different concepts of React with beautiful drawings that make total sense. So you should watch it out. Cool. So we said, well, we can think of nodes. These nodes are going to be connected. And we can think of nodes as just boxes that have a value compartment and a next compartment. So how do we start building those nodes? I'm actually just going to show you here. Let me hide. Let me see if I can move this layer. Here. Oh, I guess those two bullets are going with that. And let me put this here. So this is how we can create those nodes. We can just declare a variable like n1, and we say new node, and we pass in a value here, right? That value, as we saw here, is used by the constructor and is going to be set on the this.value property. I think I'm not, right? And what that does is, we could think of it with this representation that we have here. We created these boxes. We created this node that has the value 3 and a next of null. Has a next of null because that's what we define here. And null next. So all nodes will start with a null next. So we can think of it creating these nodes like that. So we have 4 nodes. And they are not connected at all. So, you just have nodes, that's not a linked list because, well, they're not linked. How do we start connecting these nodes?
You write the name of the variable you gave it and put dot next. I don't know how to explain it. I guess that's like a property of the class.
So, oops, can you give me an example? Like what to write here? Oh, actually no.
Yeah, no. So I would put like n1 dot next.
Mm-hmm.
Do you put parentheses?
Parentheses, yes or no?
Don't recall.
Anyone can help
Or
me?
maybe if it's not parentheses, it's equals like n2, or if it is parentheses, you put n2. I don't know.
So it's not parentheses because next is not a function, right?
Oh, okay, so you just put n1 dot next equals n2.
That's correct. So equal n2. And I remember, okay, and then here, I guess you can, somebody else can help me link. How can we link n2 to n3? Savita, what do you think?
Is it the same thing? And n2 dot next equals n3?
That's correct. And so on. So we have n next equal n4. Do we need to do anything with n4?
You can make it equal to tail if it's the last one. Unless it's the 6th node.
Wait, I think I couldn't hear who that was. Was that Owen?
No, that was Cam.
Wait, is n4 equal to? If it's the last node, then it can be equal to the tail.
Right, but in here, so we haven't introduced the concept of tails yet. We're just we have nodes and we're trying to link them. We don't need anything to do with n4. In this, now conceptually, we did this. So I'm actually gonna remove this because I have it written here. So it's the same thing, n1 and next, and then n2. Visualize at each step is we are making these connections. We're saying I want the next compartment to have a pointer to the next node. And for instance, this line and to that next equals n3, that is this connection that we have here going down here. I guess I should change colors so you can see where I'm, oops. I thought I had memorized the color change and so on. So here is, we did that with that one, we do n3 dot next equal n4, and with that we're conceptually putting this pointer here. You could also think of this as, you know, sort of imaginary strings that are joining these together. And this is what actually makes it a linked list, the fact that the nodes are connected in this way. I remember when I was doing this, I remember the first time, this was not the first way that I was imagining this in my head, because you could think that if we go back here and n1.next, this makes it look like, this was my first impression, and actually I would like for you to confirm if it might be yours as well. But this, when I saw this, what I thought was, well, it's like n2 is inside of n1 because it's inside of the next of n1. So I think at first what I had imagined like was something like, we have n1 here, and inside of n1, so n1 has the node with value 3, and in the next, you know, this is the next, this is the value. In the next is like as if we had the other one with value 5 and the null, and so on. So the way that I was imagining this at first, when I was learning it for the first time, was like Russian dolls. I think that's what it's called. Like there's one inside of the other. And any one of you also had sort of that thought? But like just this sort of thinking n2 is inside of n1 and n3 is inside of n2. So then it must be just going nested and nested. Okay, so I guess that was only me when I was first learning this. Yeah, so I think this one is not as correct from like the lower level standpoint. This is more, the linked list that we have here is more correct from the conceptual, from the actual implementation standpoint as well. It's not that there is, even this is actually even true with arrays. Like when you have an array of arrays, you know, you think that is so one array inside of another one. But in fact, what you have is something more like this. So you have an array. That's if I can write, if I can draw. You have an array, and you can think of it that you have an array inside, but you know, in memory, it's not actually like that. It's not that you have an array inside of an array. Internally, what you have is no array here. What you have is a pointer. So you have a pointer from here to another array. And same here, if this has an array inside, it's actually a pointer to some other location in memory that has the other array. So it's not that the arrays are nested inside, it's that you have pointers to other arrays, and so on. Any thoughts on this so far about the linked list or the nested arrays, pointers?
Can you scroll up to the top for a second?
Sure.
So does the constructor have a head or no? Oh, this is just a constructor for the nodes. Okay.
That's correct. So this is just for a single node. And here, so we could say that once we have this, increase the size of the node. Once we have this here, well, we made a linked list, you know, just nodes, just like a chain of any kind, of a middle chain. It's just made of single rings just join together, that makes a chain. In here, we just having these nodes in that fashion makes a linked list, and we have a linked list. We have a kind of linked list, as I think as we talked about here. There's a few ways to implement it, and we can augment this implementation. We're gonna see that in a second. But here you can, this is a linked list. And in fact, for most problems, you're gonna deal with linked lists like this. You're not gonna have like another separate class besides the node itself to deal with. Most problems actually, they just give you a linked list like this, and what they give you is just the first node, which in this case will be N1. For most problems, you're given like the head of the linked list or the first node, and you operate with that. If you have to find something, you iterate, etc. Other questions or thoughts?
Kind of a question.
Mhm.
As I'm going through projects and stuff like that, I sometimes look for the tutorials, and I just kind of noticed that you don't really get too many people who are trying to build a certain type of project using a linked list in the tutorial, unless you're looking for a linked list tutorial specifically. So is that because it's like not necessary for smaller example projects, or like is this something that just too complicated to put into the project? Like, why? I don't know. I feel like I don't see linked list anywhere really, unless we're talking about like a company. It seems kind of almost mysteriously not used anywhere.
I think it's like what all you said is true. Like for most projects, you are fine with just arrays, objects, etc. You don't need a linked list. On the other hand, it's like I think I've said this in the past. We're learning this, one, because of the industry expected of us, and two, because of the thinking of the algorithm thinking, the algorithmic thinking that this makes us go through, like very step by step. But yeah, you don't, there is not a lot of in smaller projects, and not even in smaller projects, but like I don't know. I don't think I know how to describe it. Just then, simpler and more complex projects that we use a linked list, and it's more of all this is sort of computer sciencey, and you're probably not going to use a linked list at your job, or maybe you will use one, but you don't have to create it. You're never going to have to implement it. You're just going to have methods that you call. That it's a library that is probably open source, and a ton of other people wrote that provides a linked list, and you're not going to have to write one yourself. The projects where you do find like linked list is mostly projects where are people trying to understand it, but those projects are sort of very, very specific, I guess, and very abstract as well. Like, they're not building like a web app, or they're not building, oh, here's something that just came, like probably not for front end, but in back end development, there's more room for like abstract data structures. Well, actually, I just thought of an example as well in the front end, but for instance, you have a server, and your server is under a lot of load, like a lot of requests are coming in, and you need to manage that load. So for that, you can implement a queue, right, where requests get queued, and then your server processes them at the time and at the speed that is able to. And sometimes maybe the queue gets full, and then you can't accept any more requests. But that's like an example of like a project that will use these more abstract data structures. Short answer is, yeah, most projects don't use it. And the projects that do use it is people wanting to understand them, or even more low-level projects that are more sort of computer sciencey. Mm-hmm. Other questions or thoughts? Cool. So let's see. So in this example, I think connecting, yeah. So so we can have another mental model. Oops. Making nodes, connecting nodes. Oh, I think did I? Oh, I wrote in the wrong layer. Here, let me do this really quickly if I can manage to do it. Mhm. Cool. So I can hide this. And I can show you. So that's how we connected the nodes. We could think of it also as like this other visualization I came up with here, where we have a box with a compartment of 3, and we have a next compartment that basically just holds a string to another box. We don't know that where that box can be, but we know that it's going to lead us there. It leads to the second box with value 5, and that has a next. If I go somewhere else, it goes to the next node, which has a value 1, which is out of the picture. And we don't know where out of the screen it is, but we know that that will, at some point, will connect to this node of 6 as well. So this is like another visualization like this for linked list. Like these strings going from boxes to boxes is represent those pointers, and you know that as long as you follow them, you will be going in certain order, right, etc. Now, I guess like some a question might be like, well, why is this necessary? Where we just have arrays. We want to keep a list of things, we could just have an array for that. And in JavaScript, it's a little bit hard to see that. But the problem is that in JavaScript, we have dynamic arrays, which means that you can just keep pushing stuff onto your array, and it's just going to keep growing. And it does some magic for you under the hood. I think the example that we have here, let me go. Let me close this. I think the example we have in the lesson is actually a good example that sort of explains why do we need linked lists. So here, let's say this is our memory, right? These are computer memory, and we want to keep an array that has these 3 elements: branch, Bosch, I don't know what that is, and T, right? And the next slot in memory is used by Google Chrome or by Zoom or something else. These other slots are maybe being used by VS Code or any other application you're running. And you have free space on some other places as well. Here, if we have this array with these 3 elements and we push, I don't know, dinner, the string dinner to an array, what the computer will have to do is it's going to have to move these 3 to a new location that has 4 slots available. So, so we try to add, imagining this branch, Bosch, and T are in one array. We want to add one. The computer will see that the next slot is occupied. So we'll have to move everything to another place that has the 4 slots, copy everything that was there before, plus add the one at the end. And it has to do that because this is also, I guess, this is why arrays are constant time lookup on index, because the elements are close to each other, like physically close. And the way in which you can do like, I7 and go to let's say the index is 7 and just go straight to that location in memory, is because the elements are close together, and the computer keeps track of, you can think of it as it's actually an address of the first element, And what it does is just adds, it knows how long each element is, how much space each one of those elements in the array is. And what it does, it just does a simple multiplication. It's just, okay, so if I have 3 slots and if each slot is occupying 4 spaces, and I need to go to the 7th index, what I just need to do is multiply the number of the space that each element takes by 7, and I'm going to be able to go to that address immediately. And that is why then arrays are able to, look up on the index in constant time, because it's just doing a simple multiplication to go to that index. And for that, the elements need to be, physically close to each other, because if not, then the math doesn't work. So here, if we want to add another element, the computer will need to move that. And each time you're adding something and the computer runs out of memory, it has to do that. It has to move everything onto the other into the other location. So that can become, these are sort of like not arrays in JavaScript, or in JavaScript that's happening for us and we don't realize. But that can start to take time. So that's where linked lists come from, because where linked lists, what you have is just something in one place in memory, like branch here, that just points to something else on some other place in memory that can be anywhere, and it points to Bosch, and that one points to another element like key, and these can be in any different places. The pointers are what is going to take us there, and it's going to take us in the right order. And here you see that they added like 0001, 02, 03. That's just to sort of signify addresses, basically like memory addresses. And if we have the address of the first element, we know that the first element will have a pointer, will have an address to go to the second element. It doesn't matter where it is. And the computer will be able to go there in constant time, and so on. So what this allows us to do is, well, now we no longer have to search for, when we want to add something, we no longer have to search for a continuous space in memory. We have this dynamic linked list that will still connect things in the order that we want, without having to worry about moving things around when you add an element, etc. Any questions or comments on this, on like why are linked lists helpful? So, just going back to the analogies, is imagine you have a drawer and your drawer has 4, I guess maybe a nightstand or whatever where you put your clothes on, and that has 3 drawers, right? And let's say that's a chunk of memory, those 3 drawers. And let's say in each drawer you can put 3 boxes. So you have 3 slots in each drawer, basically. And let's say if you want to add something else, well, one drawer only fits 3. So what you will need to do is search for a bigger drawer, move now 4 boxes, the 3 that you have plus the one you want to add, to a bigger drawer, right? What linked lists let us do is, well, we can have a box on the first drawer that then we lay out a string to another drawer in somewhere else in the house, where we may have 2 boxes over there, and just go like that for a few hops, and then you have a linked list. You are able to, just from being on the first drawer on the first box, following the thread, following the string, get to all of the other boxes that you might have, and be able to find whatever it is you're storing there.
I have a question.
Yep.
So is that the main benefit of a linked list, is storage, and is that why it's not really used that often because storage is really not that big of an issue?
Yeah, that's correct. Especially nowadays also, since we have like 16 gig memory computers and 8 gig memory computers, memory has gone cheap as well, yes. So that's a very good point. And at the beginning, when you have like kilobytes of memory, then that will be a big problem because you can't fit something that is too long a linked list in an array because you just physically don't have the space for it. So that's a very good point, yes.
So outside of algorithmic thinking, is it kind of antiquated then, linked lists? Because it's not a problem that we don't really have anymore.
But it's not that we don't have anymore. The problem is not the problem that it's not that we don't have the problem anymore, is that we just have gotten more memory. I think, if we think about it, yes, our computer power has increased also, but the size of the tasks and the size of the data has also increased in that regard. It's like now, I remember when like videos were a few megabytes, like now videos are gigabytes, and now there's like, I remember having a pen drive of like 1 gig. Now pen drives are like 32, 64, and hard drives even bigger. But yeah, so I wouldn't say they're antiquated. Like they still use, but that the benefits are definitely better felt on a constrained resource machine, basically, especially in memory. Yeah. So like if you're building like an IoT device, for instance, that has literally kilobytes because they're not microscopic, but smaller, then you have those kind of problems, and where a linked list can basically save your life.
There isn't a ton of application for linked lists in web applications, right? Or building a web project.
Yeah, that's correct. Maybe more in the backend, but still constrained and not a lot of application. Yeah.
Thank you.
Other questions or thoughts before we move on to like doing a question? Cool. So I think, let's see. Oops. Let me see. I think I had a few exercises here. I think. Yeah. So I think let's just do this exercise because I think is helpful. I guess here before we do that, let me show you here. So you can have, with this, you will have enough for a linked list. And as I said, the questions that you're gonna encounter mostly just deal with a head node, and that's it. You have nodes, and you are guaranteed that they're gonna be connected. You don't have to do the connection yourself manually. But if you wanted to create, if you didn't want to have to link each node individually like we did here, this, what happened? This becomes, but I learned how to fix that today. Here, if this is not a very practical linked list in the sense that it's not easy to add a new thing, right? Like here, if we want to add a new element, we first need to create it here, like N5, and then make the connection ourselves manually, right? So this linked list, even though this is the linked list that you're going to be dealing with the most in your programs, in your questions, it's not very practical from like if you want to use it. Like you can solve problems with them. You're going to receive this linked list for your problems. But if you want to add something else, if you want to find something, it's not very practical. So what we can do is, oops, let me see what else. Did somebody just come in?
Yeah, it was me.
Oh, okay.
Sorry.
Cool. So that is not very practical, but what we can do is have a helper class, the linked list class, and that will look something like this. we have a linked list class, and we could think of it as in terms of boxes as well. We can see this visualization of our container. We just have a slot for a head, slot for a tail, and a slot for keeping track of the length, right? And I just drew these like circles there just to signify that it can be anything. Currently, they don't have anything. We can see just that we have some like head part, tail part, and length part. And then what we can do is say, just to augment our linked list and have it more easier to handle, we can just add some methods to it. So we can have like add first, add last, add at index, contains, where we could just, you know, call our linked list method add first and pass in a value and have that value being added to our linked list without us having to manually create a node and manually connect that node. This function can do it for us. Same for at last. Let's say we want to find something in the linked list with a contains that returns true or false. We could also write that there. And you know, why a linked list class? Because of ease of use, basically. Keeping track of key information like the head and the tail and the length. You know, the nodes in the middle might not be as important for your problem or in general, but the head and the tail might be important. For instance, to allow constant time access at the beginning of the list and at the end of the list. Super handy to have a head and a tail reference that we have in our box. Also, you want to keep track of how many elements you have in the linked list. The length for that, and methods for handy adding, removing, handy operations on the linked list. If we have here, and then I think this is something I forgot to type here. If we want to create a linked list now, what we could do is, let me type in this. Yeah. What we can do is say let ll equal new linked list. We create a linked list like that, and then we can say ll dot add first. And let's say we want to add node with a value of 3, and so on. We can just keep calling this function, and this will start to create the nodes internally, as well as connecting them, so that we don't have to do it manually like we did here on the right. So this is where you might see the linked list class. Also, you know, everything we can do with the linked list class, we could do without, but it is for ease of use, basically. Let's say, you know, if we want to add a thing to the, a node to the end of this linked list, we can do it manually. What we could do is write a function that only takes the head, goes all the way to the end, and adds it there as well. But, you know, why a linked list? Simply for ease of use. Also, like, you know, thinking of our visualization here with the boxes. The linked list is just a container that to 2 pointers, basically a head pointer and a tail pointer, and that can just look like here. This will point to this first box. The tail points to the last box down here, and that's it. It's a box with some strings to some other boxes, and that makes the whole thing. Questions or thoughts about the linked list class? So we're gonna see an example here. I think we're running out of time, but this example where the contains, here we're gonna do it like, we're not gonna do it in the linked list class. And I think for this, I'll just demonstrate it because I think I wanted us to have some time for you to try it out. but let's implement the contains method, but on without the linked list class, basically only with this linked list that we built here. And let's see what that will look like. So I'm gonna go here. Let's go to repl it. And I'm gonna show this after. I guess I should have this code written. Node constructor val is that val equal val. That next or no. That n1 equal to new node 3 to does anyone remember the next node? 3. And this is 5. Oh no, this was 1. This was 6 and 4. 2, 2, 3, 4. We have a linked list here with this already. Oh, this was why I thought that this was like Russian dolls basically nested, because when I console log n1, which is the first node, n1 is our head. This is what I thought that was like a Russian doll, because when the console log is I'm getting the node 3, which is the head, or the node with value of 3, and inside I see the next, and the next has another node with value of 5, and the next of that node has another node with a value of 1, and the next of that node has another node that, you know, just JavaScript got tired of printing, and it said just node here. So that's the thing, that this is where I got that initial image from, like, well, this seems to be nested. But conceptually, it's more of like the boxes with pointers. It is that console log, what it's doing is just following the pointers, basically, to print it out. So we have our linked list here, and we saw that if we want to add a new node, it's kind of cumbersome that we have to do this. But let's say we want to implement a contains function. And what we want to do is we want to check if our linked list has any particular value and return true or false if so. So this contains function, we're not going to implement the linked list class. So for this contains function to work, we'll need to have we'll need to pass in a node, which is going to be our head node, and what value to look for. Let's call it value. Right, and we said, Cameron said, well, to find something, you need to iterate over the linked list, visiting basically every single node. That's what we're going to do here then. So to iterate over this linked list, and also let's imagine, imagine you only have access to the head, or to n1, which is the head. So, you know, we know what we're going to do is we're going to call this function, and we want to see if the value 1 is in anywhere in the linked list. We know that it's here, it's in node 3, right? But let's imagine that we didn't have access to these variables. Let's imagine that we only had n1 and we had to follow the pointers to try to find that. Any ideas how we could do that? How can we follow the pointers?
You need a tracker.
I need a tracker. So tell me what to type here.
Like you can say let current equal node, like that would be the head that you first taken.
That's correct. So this will be our tracker, I guess, current. Okay. Let's So we need a tracker. What else?
And then you can loop.
A loop, right? And somebody else, how do we loop over a linked list?
As well.
A while loop.
The condition can be set to making sure that the value isn't null, so you want to end before the last node.
That's correct. So we want to go over, we want to move from node to node. We want to go to, basically, we want to follow the strings in these boxes as long as the strings are leading us somewhere, right? At some point in, for this node N4, the next is null, right? Because that node, we don't connect N4 that next to anything. So we want to check for whenever the current node we're on, next is null. That's one option. I think this is where it gets a bit tricky, but let's run with this. So I'm gonna say while current is not null. So this is saying, okay, let's keep going. Let's keep moving current as long as it's not null. And we're gonna see that as we're following the links, it will become null at some points. And let's then do, yeah, I guess let's do console log first. Console.log current. So let's console log current here. And let's run this. Let's type in N1 as our head. Oops. This steals my focus when somebody joins. And for value, let's just pass 1. This contains is not defined. I think I have a spelling mistake.
I think the current in the while loop.
Oh, yep, that's a good point. So if we run this here, oh, current is not defined.
Yeah, the U.
Oh, thank you. Spelling mistake, our friends. So we run this, we have an infinite loop.
Oh, that's funny. Just typing it out.
We have an infinite loop, and we're console logging current, right? Because, well, current is just going to be the node that was passed, which is N1. And we're saying, well, current is not null. Well, that node is not null. The node is the node itself. We console log current. So what we need to do is move on to the next node. How do we do that? How do we move? So current is just like another pointer pointed to our node, and we need to move into the next thing.
You can say current is equal to node.next.
Current is equal to current.next.
Yeah, current.next.
So whatever current is in the next value. Let's try this out. Let's see if we get a different result now. I guess that's if my computer recovers. Okay. Because we have an extra console log here. Let's redo this. Here's what we get. We get the first node, console log first. The second node, node 5, node 1, node 6. So we're console logging each node at each step. And so on. So this is then how we, I think, see if I can draw it in a few minutes. We're moving over the list here. If we wanted to print the values, we can just do current.val instead of printing the node, and we should be able to see the values in the node. We created them in the node, we linked them, which is 3, 5, 1, and 6. And here we were just interested in finding if that value was there, so we could just say if current.val triple equal the value we're looking for, let's return true. Otherwise, if we went through the end of the linked list and we found nothing, let's return false. And always we want to move on to the next. So you could think of it, you could think of this current equal current dot next as sort of the I++ in a for loop for an array, right? That's how you move on to the next thing. And here in linked list, this is how we move on to the next thing. We reassign current to be current dot next. If we have this, then we run that, we get true. We left the console log. We also see, for instance, that we never go to 6 because we found it earlier, and return will quit. Let's put a number that doesn't exist. Run that, returns false. It went all the way to the end. We see every number console log, and it returned false because it didn't finish. So just for us to have a sort of mental model of this, let me go back to the drawing board and that'll be it. So we basically have a, let me try to make some room here. Actually, that's going to be tough. We have a current pointer that is pointing to the first node. That's how we start. We check if this is the current value equal to the one that we were searching for. It is not. So what we do is we reassign current to point. This is current. So current dot next. The dot next will be this of current, right? So what we do is just reassign current to be the next node. So we move it here. And then we check if this is the value that we're looking for. If it's not the value, we reassign current to the next, to point to the next node, so to point to current dot next. We check if that's the value. In this case, in our first example, that was the value. It will quit there. But this was that current. It's just a pointer. It's just a variable that's holding a reference to the node. And we keep moving that. We need that tracker, as Brianne suggested. I guess any questions, thoughts, concerns about this? The code and also sort of the mental model.
That only works for a single linked list, right?
That is correct. You will only work for a single linked list. Oh, actually, let's think about it. It will work for a double linked list as well, because the double linked list, the difference between a double linked list and a single linked list is that you have here that previous that starts null. And when you do is, well, when you're connecting next, you also want to connect the previous. But the double linked list will still have a next. So our algorithm will still work because we're moving through the next. The linked list will let us move, like, the cool thing about the linked list is that it will let us move back and forward. So we can have, from the single linked list, we can only move forward to the next. So the double linked list, we could come back if we so needed. Mm-hmm. But it will still work for a double linked list in this case. Other questions? So my recommendation is to go to the whenever you want to study this stuff, the Pursuit Core Data Structures and Algorithms curriculum, right? You can find this in, you just go to Join Pursuit. It's one of the pinned repositories here on the right. You can also find it in Canvas if you go to the syllabus of our course. But here, this is standard reassessment. So if you want to reassess linked lists, what you need to do is just answer these 5 questions on linked list. Come to us. We will do a mock interview with that. One of these is, for instance, palindrome. Let's take a look at this one. Right. So this is just like, if doing a single linked list determine if it's a palindrome. Basically, if it's the same backwards and forward. And you can see here that what they're giving you, they're not giving you a linked list class, they're giving you a linked list node. And it's just that it's not running with a class because this is older ES5 JavaScript. This is a factory function, which is the same stuff as a class, basically. And it has this.vol, this.next. They're just doing some stuff here saying if you don't pass a value, the value will be 0. If you pass a value, the value will be the value that you passed, etc. But you just get that. You get the nodes that we were talking about. They're exactly the same, the ones that we wrote. And then here you have to find if the linked list is the same backwards and forward. But I guess like the main point I wanted to make here is that the linked list is just made up of nodes. There's no linked list class. You traverse it in the way that we did here. So I'll encourage you to go check these problems out. You know, if you have questions, reach out as always. And yeah, that will be it. I'll make sure I share this these drawings. Any final questions before we break off? I'm sorry we didn't have like a lot of time for actual practical, but I hope that this provides a little bit more of a mental model for how to think about linked lists and a way to visualize them. Cool.
Thank you.
Oh, Alejo, I have one more question.
Yep.
What are some other ways that, like, what are some other methods that we might see, like, when using, like, implementing a linked list? It's like, say, in like a whiteboard interview.
Yeah, mostly there's the ones that we ask here. This is a lesson. This is a linked list lesson, right, in our curriculum or PSA. Mostly like adding. Here I call them push, append, print, node at, pop. The names can be anything. Like you can make up these names. These names were made up because it's an abstract data structure, and we said, you know, there's no. It's our job to implement those, and you know, we can see here push. This is how we're pushing a new node. So appending to the end. So push is like pushing at the beginning, I think, and append is appending at the end. I was looking at here, for instance, this is Java's documentation. Java does have a linked list class, and look at how many methods it has. It has add. I don't know if you guys can see that. It has add, another version of add all, add first, clear, clone, contains, etc. But I think just the basic operations like adding and removing, finding, adding, removing,